So in this video, we're going to talk about buffers. All right, so buffers is a substance that is resistant to drastic pH changes. All right, and so most specifically, a buffer is usually a mixture of a weak acid and its conjugate base, or it's the weak base and its conjugate acid. All right, so let's kind of talk about how does this work, and I'm just going to give you like an example of how mixtures of weak acids and its conjugate base, or a weak base and its conjugate acid, acts like a buffer, or acts in such a way that it tries to minimize as much as possible, or it is resistant to huge pH changes. All right, so let's look at an example. So let's just say you had a solution that contained 0.10 moles, or molarity, I'm sorry. So 0.10 molar of acidic acid and 0.10 molar of acetate ion. So here is the acid, here is the conjugate base. All right, so they're about equal concentration. So this makes it a really good buffer. All right, so how does this resist pH change? All right, so in a nutshell, all right, so what basically happens is that if you were to add a base, right, you add a base, you add a hydroxide, okay, the acidic portion of the buffer is going to react with the base to form the conjugate base. Okay. If you were to add an acid, right, then what's going to happen is that the base portion, or the conjugate base, or the base portion of the buffer is going to react with this acid to form the conjugate acid. All right, and then so basically by this you're keeping the pH, you're keeping the solution from changing its pH drastically. All right, and because you remember, pH is the measurement, the logarithmic measurement of the concentration of the hydroxide. So if you could take hydroxide or hydronium, so pH is equal to the negative log of the concentration of hydronium. If you could take hydronium or hydroxide or new hydronium hydroxides out of the solution, then the pH won't change much. All right, and that's basically the job of the buffer. All right, and so let's kind of talk about how does this take place. Let's look at the chemistry. And so if we have a weak acid, so HA will be our weak acid. The H is the hydrogen, A is the conjugate, right? So weak acid, all right, and water will form the conjugate base, which is aqueous, plus hydronium. This is your conjugate acid. So let's go ahead and label this. So this is your weak acid. All right, so that makes this your conjugate base. All right, and then in this case, this will be your base, and this will be its conjugate acid. Okay. Now, because it's in equilibrium, we could definitely write the equilibrium expression for this. In this case, for Ka, and this is a liquid, aqueous. So Ka will be the concentration of the hydronium times the concentration of the conjugate base divided by the concentration of the weak acid. Okay, it's the products divided by the ratio between the products over the reactants. And just remember, you don't ever include anything that's not an aqueous or a gas in the equilibrium expression. Okay. Now, as I said, the concentration of hydronium, all right, is what dictates the pH. All right. And so if I were to reorganize or rearrange this so that it's equal to the concentration of hydronium, then we see that the concentration of hydronium is equal to Ka over the concentration of Ha over the concentration of the conjugate base. So it's the Ka times the concentration of the weak acid times the concentration of its conjugate base. All right. Now, as I said, we know that pH is a negative logarithm of the hydronium ion. All right. And so pH is dependent on the concentration hydronium ion. Well, in this case, if we're talking about a buffer, all right, and the way the buffer works, the hydronium ion concentration is dependent on the ratio of the acid, the weak acid, and its conjugate base. All right, and so you could kind of rearrange this again, where you have basically pH is equal to the negative log of the Ka over the concentration of Ha over the concentration of its conjugate base. So as I was saying, the pH is dependent on these two. Now, if you were to think about this chemically, right, if you were to add a base, right, if you were to add a base, you're going to decrease this because the weak acid is going to react with this base. All right, and the equilibrium is going to shift to the right. When it shifts to the right, you're going to make more conjugate base. So if you think about this ratio that we're going on here, if we were to add a base, we're going to decrease this, but at the same time increase this. All right, and so then what's going to happen is that the ratio is going to be roughly the same. All right, as long as these two numbers don't change much. Okay, and then it's the same thing if we were to add an acid. All right, if you add an acid here, then the conjugate base is going to react with the acid. All right, and so this is going to decrease. All right, and then the amount of weak acid will slightly increase. All right, now key point though, that as long as that's the change between these two initially and after the adding of the base or the acid is relatively small, all right, the changes are very slight, then there's going to be very little change in the pH as well. So that's why this acts like a really, really, really good buffer in this case. All right. And so when you consider and you think about the strength and the scope of these buffers, well, if you had, like, for example, pure water. All right. So if you were to have pure water, all right, and you were to add 0.010 mole of an acid, okay, you will see that the pure water, its pH will go from 7 to 2. All right, just by adding 0.10 moles of this acid. All right, but if you have this acetic acid and the acetate buffer, so we have this buffer, and you were to add 0.010 mole of the same acid, all right, we'll find that the pH will go from 4.74 to 4.85. I'm sorry, take that back. It's an acid. So it's going to go to 4.68. All right, so you see here, because of the buffer, it doesn't change much at all. All right, the buffer starts here and it ends here. All right, so that's how buffers work. So another way that we could quantitatively look at buffers and study buffers and look at the changes of concentration is using what we call the Henderson-Hasselbach equation. All right. And basically where it tells you that the pH is equal to the pKa plus the log of the concentration of the conjugate base over the weak acid, over the concentration of the weak acid. Okay. Now let's kind of talk about just pKa real quick. pKa is just basically the negative log of the Ka. All right. So it's just a logarithmic function of your acid dissociation constant. All right. So to find the pKa, if you have the acid dissociation constant, you take the negative log of that, then you will have the pKa. All right. And so let's just kind of talk about what all this means and what data and what information we could get. Well, if your pKa, all right, is close to the pH of the solution, then you got yourself a pretty good buffer solution. So, as I said, the pKa of your acid, all right, your weak acid solution, you want that to be as close as possible to the pH. And if that's the case, then you know you definitely got yourself a good pH. I mean, a good buffer solution. All right. So you also wanted that the ratio between the weak acid and its conjugate base should be close to 1 as possible. And so if you have this ratio between these two to be as close as possible, then at the same time, as I said prior, you have yourself a pretty good buffer solution. All right. And so if you were to add any acids or base, as long as it's small amounts, then the pH of the solution should not change dramatically. Okay. So let's look at an example problem. The question is, what is the pH of a buffer solution that contains 0.100 molar of HF and 0.120 molar of NaF? The Ka of HF is 3.5 times 10 to negative 4, and the pKa is 3.46. All right. And so in this case, we're going to use the HendersonHasselbach equation, where it's just pH is equal to pKa plus the log of the concentration of your conjugate base over your weak acid. Okay. And so in this case here, we are looking at the pKa plus the log. So we will see that the conjugate base here is your fluoride ion, and the weak acid is hydrofluoric acid. Okay. And so these are your concentrations. All right. And so let's go ahead and highlight what we have. So it tells me the concentration of my weak acid. All right. You gotta know the concentration of your the conjugate base here. All right. It tells me what's my Ka value, and then it tells me what's my pKa value. Okay. So really, we don't really need Ka. The Ka was just to help us to figure out what's the pKa. But since we know the pKa, we can actually plug this all into this equation here. All right. To where our Kas will go here. Okay. Then our concentration of HF, all right, will go here in the bottom, and the concentration of F will go at the top. Okay. And so when we plug this into our equation, we get pH equals 3.46 plus the log of, and so the F is really 0.120 molar, and the bottom is 0.100 molar. Okay. And so if you put this in the calculator correctly, we'll find that the answer would be 3.54. All right, so then what you see here, now we see that the pH of this solution is 3.54. The pKa is 3.46. So the pKa and the pH are roughly the same number. So this tells us that this is a really, really good buffer solution. Okay, so this is buffers.